Now, based on all of these different background test methods that I talked about, there is a general consensus that's come amongst the researchers that we need a combination of different test methods to come together to give us a clear indication of the reactivity. There is no one single test that can actually help us understand reactivity. So, one needs a combination which looks at lime depletion, which looks at strength enhancement, which looks at heat evolution during the reaction and so on. We need to combine several different parameters together to really get a clear assessment of the test of the reactivity of supplementary materials. So, in this case, one of the common ideas that came out of several series of tests done with RILEM TC267 and also an ASTM report was this R3 test method. R3 essentially means rapid, reproducible and relevant. So, R3 was generated based on the work done in the RILEM TC committees by Ruben Snellings and Karen Scrivener, and this was essentially started off as a test done for calcine clays, but later also extended to other supplementary cementing materials. Okay. And this was also standardized later in ASTM C1897. It turns out that even after this R3 test has been proposed, there has been several modifications to the same also. Okay. And as I said, this is a subject of much debate, but it has been universally accepted that yes, we need a combination of tests to actually represent the true reactivity of the pozzolans. Now, here interestingly, the system does not really involve a plain lime pozzolan system. This is a modified lime pozzolan system in which what we do is we have the supplementary material that you want to test along with portlandite or lime, calcium hydroxide at a ratio of 1:3. Okay. Then you have deionized water along with a mixture of chemical ingredients like potassium hydroxide, potassium sulfate and calcite. Why are these introduced? Because we want to create an atmosphere which is similar to what the pozzolan will have in a normal cementitious matrix. When you are mixing the pozzolan along with the cement, the chemical environment will have alkalis, will have sulfates and we may have some carbonates also in the system. Okay. So, in such a system, what we do is we test at a temperature of 40 degrees for a duration of 7 days. Now, what we are trying to assess in this test is thermogravimetrically how much of this lime gets consumed, how much of this portlandite is getting consumed by the pozzolanic reaction. Okay. So, the R3 test performed at 40 degrees for 7 days to facilitate better degree of reaction from the SCMs, paced from the heat of the hydration study. So, we do a heat of hydration measurement using a calorimeter and we take the same paste and we do thermogravimetric analysis to measure the extent of bound water and the consumption of calcium hydroxide. What is bound water? Again, water that is bound within the structure of the hydration products. That means water that you can't evaporate from your system. By simply drying at 100 degrees, this water does not go away. It only goes by igniting it at a higher temperature. Okay. So, you determine bound water, you have to determine the heat evolution and you have to determine the portlandite or calcium hydroxide consumption. Obviously, this test is a lot more evolved than anybody can do in a simple quality control lab, but I will come back to that also. So, again here what is seen is the heat release in the R3 test plotted as a function of time. Okay. The more reactive materials are going to release heat much faster, right. They are going to release heat much faster. The less reactive materials like type F fly ashes will release heat much slower as expected, right. So, it is very clearly bringing out that distinction between inert materials which do not release any heat versus slowly reactive pozzolans like type F fly ash versus very highly reactive pozzolans like calcine clays which are right on top here. This red curve is that of calcine clay and the violet curve is that of slag. Okay, that's CC and that's slag. Okay. Now, the heat release in joules per gram of the supplementary cementing material used seems to correlate very well with the bound water content. If you look at this curve here, this graph here, the linear correlation that is drawn here has a significantly high correlation coefficient of 0.89. or regression coefficient of 0.89, and what you clearly see is that there is a distinct increase in the extent of heat release with the bound water content, and that is only natural. Heat is getting released because of the reaction, and bound water content also goes up as more and more reaction happens and more product gets created. So, there is a clear correlation between heat release and bound water content, and not such a good correlation between the Portland rate consumption and the heat release. So, you see that this linear trend does not produce a very good result in this case. Okay. Now, what happens is not all of the pozzolanic material gets completely dissolved in your system and react with the lime that is available. So, Portland rate consumption, there is a limit to what you are actually getting there. Okay. But what you can see is that if you can look at the extent of heat release and quantify that as 100 and below being inert materials, mainly these are your quartz powder, for instance, right. If you take quartz, crystalline quartz as an inert material, you have less reactive material. This will probably include your fly ashes and maybe some slags, but mostly just the fly ashes are type F and type C fly ash. Okay. Then you have the slags and the calcined clays, which are in the more reactive system, where your heat release is greater than 450 joules per gram of the SCM. Here, greater than 100 joules per gram. So, what essentially this helps you do is that you can classify your material as being inert, less reactive or more reactive. But again, the consumption of calcium hydroxide is not really telling you a true story here. It is not telling you a story that you would like to see with respect to a perfect correlation with your increase in the heat generation rate. Okay. So, R3 test method generally is shown to be more reproducible as compared to the Frattini test, and there is also another test method. Of course, everybody would like to create their own tests, but most of these are just chemical tests which look at evolution of pozzolanic activity with more and more lime consumption. Modified Chappell test is another test which is used quite often by researchers, but it shows that R3 test has a much greater reproducibility, and because of that, some form of R3, either in the original form or modified form, people are employing in a large way to extend to all kinds of supplementary materials. So, in conclusion, with respect to the activity testing of materials, it is very important for us to adjudge the extent of reactivity shown by any mineral additive or supplementary material before we start using it in concrete. We can't really take a material which is newly created and start putting it as a replacement of cement in concrete without assessing what it can potentially do. Because if the material is inert, you are not going to be able to replace cement with that material. But what would you do with an inert material? Sorry? You can use it as a filler, as a portion of the fine aggregate. You can replace the inert material, right? If the material is extremely fine, you can consider it as a part of the cement paste also. Let us say the material which is a filler has size ranges of much less than 75 microns, then technically you do not qualify that as a replacement of aggregate. You can take that as an additional cementitious material, but something that is not going to react. Okay. On the other hand, the highly reactive materials like silica fume or high purity metakaolin, again you are restricted with respect to the extent of replacement you can do with the cement. Why? Why can't I replace a lot of my cement with silica fume? Okay, heat of hydration mostly goes up because of the extreme reactivity of cement. High pozzolanic materials also will contribute to that, but that may not be the reason why we can't go for extremely high contents. Why don't we want to go for a much larger content of replacement? They are highly pozzolanic, no? Lot of active silica is available, but is there enough lime available in the system? there is not enough lime available in the system. Of course, there are secondary effects also, because many of these materials are extremely fine, because of which they will increase your water demand significantly, and it will not become practical to replace cement so much with silica fume or metacolum. On the other hand, when we talk about slags, which are nearly of the same particle size as cement, right, which have a reactivity which is moderate and almost similar to cement but slightly slower, you can think about replacing much larger contents, also because slag is called a latent hydraulic material, right. Slag can react on its own with some activation. Fly ash, again, the reactivity is limited, because of which if you are looking for concrete that produces the early age strengths, your extent of replacement also is going to be limited. But on the other hand, you can take advantage of the slow reactivity of the fly ash and use it in larger quantities to produce concrete that evolves less heat, reduce the heat of hydration significantly. Okay, so depending upon the application that you want, you have to make a judicious choice of what is the best mineral additive to use. Of course, apart from this, the availability will be a big factor which will define which additive you get to use, right. Something needs to be transported over a long distance, it is going to add to your cost. So, it is not really something ideal that you want to use in your system. Now, when you make concrete with it, okay, when you make concrete with the mineral admixtures, replacing your cement, you can consider various different ways of accommodating the volume brought in by the mineral admixtures. So, you can use the material either as a replacement for the cement, or keeping the cement there, you add additional quantity of your material. So, for instance, when you are doing normal grade concrete like M20 or M30, we are looking at these materials as a replacement of cement. We replace cement partly. But when we are talking about high strength concrete, we need a lot of cementitious material in there. We are not going to be replacing cement. We are probably maximizing cement. How much is the maximum quantity of cement that we can use for building purposes? 450 kilograms per cubic meter, right? As per the IS 456, we can't exceed cement content of 450, but in certain instances, for let's say for producing self-compactable concrete, you may not be able to do just with cement. You have to extend it using mineral additives, okay. In such instances, we use this as an addition and not as a replacement, okay. Now, what will happen as a result of this is that your volume adjustment has to be done for the concrete, because concrete is always designed for a given volume. You design concrete for 1 cubic meter, and what is the approximate mass of that 1 cubic meter? What is the mass or unit weight of 1 cubic meter of concrete? 2400 kilograms per cubic meter, right? Each cubic meter of concrete weighs 2400 kilograms. But what will happen is, if you replace cement, let's say 50 kilograms of cement is replaced by 50 kilograms of fly ash. What's going to happen to the volume of the system? Which is denser, cement or fly ash? Cement is denser. Cement has 3.1 density, whereas fly ash has about 2.2. Siliceous materials are between 2.2 and 2.6, okay. So, you are replacing a heavier material with a less denser material. So, what's going to happen to the volume? It goes up. So, volume of the paste is going to go up. So, what will you do now? How will you compensate? You will have to probably look at other batched ingredients like fine or coarse aggregates. You are removing some volume from that to keep the overall volume the same. But how? Now your system has changed. Why? Because earlier you had a certain volume of paste to volume of aggregate ratio. By replacing cement with a less denser material, you are upping the volume of paste, and to keep the total volume constant, you are lowering the volume of aggregate, right. So, that will produce some effects in your system. What effects will it produce? Sorry? Strength may or may not get affected depending on the water cement ratio and how you design your mix, but shrinkage is going to be affected. Creep may be affected because you have more paste and less aggregate. So, you have to be careful in your design methodology to not exceed or rather change this paste to aggregate ratio significantly if you are looking for similar properties. You can always design for other properties, but if you are looking for similar properties as that with plain Portland cement, you have to do it more judiciously. So, there are other ways of proportioning also recommended, like modified replacement or efficiency factor method. Efficiency factor is not easy to apply on site. Okay. So, what happens is in a modified replacement, you consider part of the mineral admixture as a replacement of the system, part of it as an addition. So, let us say you have 400 kilograms of cement and in mix 1, and the second mix you put 320 kilograms of cement plus 150 kilograms of fly ash. So, what I am trying to say is part of this 150 is taken as a replacement for the cement, part is taken as an addition. So, instead of designing with exactly 400 cementitious material, now I am designing with 470 cementitious material. So, I am going to alter my design and make sure that I am able to get the same hardened concrete properties. Efficiency factor tells you that if I replace 1 kilogram of cement by 1 kilogram of fly ash, what is the efficiency of that 1 kilogram of fly ash? Does it produce 50% of the cement strength or does it produce 100% of the cement strength? So, that essentially implies, can I replace the same mass of cement by the pozzolanic material and still get the same performance? Okay, that is not easy to predict, no. First of all, it will depend on the age at which you are testing your performance, because fly ash, 1 kilogram of it as a replacement for 1 kilogram of cement may produce the same equivalent strength at 90 days, but at 28 days it may not do that. So, efficiency factor is a little complicated to apply in practice. For the most part, people simply do the simple replacement or simple addition. That means replacement of the cement by volume or by mass. Now, I have said two things here, replacement by volume or replacement by mass. If you do replacement by volume, what will happen? So, I am removing, let us say 400 kilograms of cement is my overall cement content in the mix 1. In mix 2, I have 350 cement and 50 kilograms equivalent volume of fly ash. What do I mean by that? I have removed 50 kilograms of cement and whatever volume that created in my system, that much equivalent volume of fly ash I added. So, what happens to your paste to aggregate ratio? It does not change because you are volumetrically replacing the system. Okay. But again, in the field, if you think about it, it's a lot more complicated. For that, you need all these values, right? You need to understand the specific gravities of each of the ingredients. You need to have some idea about working with volumes. That's why in the field, people generally work with mass replacement. Mostly, we work with mass replacements or mass additions of the cementitious system with fly ash or slag or any other mineral admixture. Okay. So, it's very important for us to keep track of how this will affect the overall characteristics, because it's going to adjust your paste to aggregate ratio. So, when you see the results and start comparing, make sure that you are able to clearly understand what is the impact of increasing the volume of the paste on your system. Very often, we see that when shrinkage results are given, comparative shrinkage performance of plain cement based system or pozzolanic system is given. Very often, this issue of change in paste to aggregate ratio can lead to a major change in the way that you interpret the results, or can lead to a major change in the way that the performance of concrete with respect to creep and shrinkage actually happens. So, we will come back to that a little bit later when we talk about performance. I think we are done with time for today. So, we will stop. Yeah, well, I will come back to this and finish up in the next class.